Okay, so the goal of this video is just to show one more example of a logistical growth model in a differential equation, and so very similar to maybe some other examples we solve, but just to see, maybe you want to see one more example, which is great. And it tells us it's a logistical growth model, and we should recognize a logistical growth model based on the structure of our quadratic. And even if you factor that 0.0008 out, right? Because we want to isolate the quadratic term, we're going to get that characteristic shape or structure, I should say. So we could say that our dp dt is equal to, if we factor out 0.0008 and then a p-value, we end up getting 250 minus p. And so now I definitely see that characteristic structure of a logistical growth model, where it's the product of how much is present times how much is left over from that carrying capacity. And that tells me that 250 is my carrying capacity. And the carrying capacity answers the question, what is the limit as t goes on to infinity, which is kind of a cool way, I guess, a cool way to think about this, that we can answer a limit not even given the function, let alone t, right? This is all in terms of p. So that this is finding the carrying capacity, recognizing it's the carrying capacity, so we know that's 250. Now, when is the population changing the fastest? Well, we might not be able to find the time just yet, but we do know it happens when our population is exactly half the carrying capacity, which is 125. And thinking about when this derivative is zero, this derivative is zero at 0 and at 250. But remember, those are p values. So if I'm drawing this graph, I know that, if this is time, and this is our p-value, which is our y-axis. So at 0, there will have to be a horizontal asymptote. At 250, there'll have to be a horizontal asymptote, and it does give me initial condition of 0.50, so right through there. So the graph that would model this growth will look something like this. And so it's bound between those two values, that horizontal asymptote at 250, horizontal asymptote at 0, which means when does it achieve its fastest growth? Oh, I thought I picked a different color. Right there at this point of inflection, right, which is going to be exactly halfway between 0 and 250, which is 125. So even though we don't know when it is, at least we know what that value is when we get to solve. Okay, so let's go ahead then and let's go ahead and solve this. So let's go ahead and separate the variables and bring over the p-values to the left. So it's 1 over p times 250 minus p, and that's going to be dp is equal to 0.0008 dt. And you should be verifying that this is not a simple u substitution on the left, because it's a second degree but a constant on the top. And then we should also know that it can't be inverse tangent because it's a negative quadratic, and it can't be inverse sine because there's no square root. So it's going to be partial fractions. And so we want to break those two up into some amount over p plus some amount over 250 minus p dp equals the antiderivative 0.0008 dt. So, some of you are going to get really good at this and finding those missing coefficients, and they usually are the same value, especially, I can't find my center, especially when in the denominator, one is a positive, one is a negative. So that corresponds to whatever you put here. When you multiply by that negative p, it needs a positive counterpart to cancel it, because all you have is a 1 up there. And oftentimes, as in this case, it's going to be the reciprocal of that coefficient, like that 1 over 250. So that happens to be our carrying capacity. So there's a lot of similar things that are happening in the structure of solving these problems. So I want to make that a 1 over 250 and a 1 over 250. So that when I integrate, this is 1 over 250 natural log of p minus, because of the chain rule, 1 over 250 natural log of 250 minus p. So that's going to equal 0.0008t plus our constant. Now, let's clear our fraction and put our logs together at the same time. So we have natural log of p divided by 250 minus p is equal to, and if you multiply the 250 across, you do have to take care of that. So now we're back to our 0.2t, but then we can just rename our constant a different constant. And it's at this point I would probably e to the, because you've got your log together, and when you e to the, now we get just with no absolute value, p over 250 minus our p value is equal to new constant e to the 0.2t. I would probably insert our given condition, right? When time equals 0, our p-value is 50. And I think what I might do is I go to maybe the black pen just to show up here. So that is if I switch to pen. So there it is. So p we said was 50, and 250 minus 50 is 200. Is equal to c e to the 0. So we do end up getting 1/4 is equal to my constant. So I have p divided by, I should say, 250 minus p is equal to 1/4 e to the 0.2t. And we want to get our p-values by themselves. So one thing that we can do, is they can switch spots. So this can be p divided by 1/4 e to the 0.2t is equal to 250 minus p. And so I can simplify this. The 4 could flip up. So it could be 4p divided by e to the 0.2t equals 250 minus p, and I can easily bring that up by just making your exponent negative. Oops, that's from another class period. Sorry about that. So I'll erase that. There we go. So let's do that. So this becomes 4p times e to the negative 0.2t is equal to 250 minus our p value. Let's go ahead and add the p over. So p plus 4 PE to the negative 0.2t is equal to 250. We can factor out our p value, so it's 1 plus 4 e to the negative 0.2t equals 250, and now I can divide that quantity over. So it's a little bit different than what we did in class yesterday, but I think it's more efficient. 1 plus 4 e to negative 0.2t. And what I like about this is that it gives you your carrying capacity right there in the numerator. And so as you can see, the limit as t goes into infinity, if you let t go to infinity, then this becomes like an exceptionally large negative, which is an exponential as a reciprocal, which gets close to 0, which basically makes this term go to 0. So we do get 250. So we knew that. Okay, and then we want to answer the part C is when is it increasing the fastest, which is exactly halfway. So that's when it's 125. Oops. So let's go ahead and set the population to 125. So that's 250 over 1 plus 4e to the negative 0.2t. Now we can take this expression, put it to the left, move the 125 to the right underneath it. So that's a 2. So we get 1 plus 4 e to the negative 0.2t is equal to 250 over 125, which is 2. Subtract the 1. So now we get 4 e to the negative 0.2t is equal to 1. And then divide out the 4. And then take the natural log. So now we have natural log of 1/4 is equal to negative 0.2t, and then we can divide by negative 0.2. And no worries that you're dividing by a negative, because natural log of 1/4 will also be negative since it's less than 1. So natural log of 1/4 divided by negative 0.2. So I have a value for t equal to 6.931. I don't remember if I gave a unit for time. Is it years, months? It doesn't really say, so it would just be units of time. And since time is continuous, we can leave it to 3 decimals. But if it's asking for like something about the population, then you would round to the nearest whole number for that value. So okay, yeah. So again, when you get really good or familiar or used to solving these growth models, then you sort of see the pattern and you see the structure and the procedure for each of them is relatively the same.